All right, it's 11:15. I think we'll get started. So section 5 is open in OneDrive, so you can check out the notes. I just put them up this morning. Sorry, I was trying to push through grading, but there are new notes in section 5 on OneDrive, so check those out. There's one more homework that I'll post that's due next Friday, PLAs, etc. And so we have today's class and 3 more, and I will show you some slides to review for the final as well. So we are going to cover new material, but remember there's only about 3 lectures of new material, and so it's going to be less than 10% or 10% or so of the final. So the final is not going to emphasize one section versus the other. It's going to be pretty evenly distributed across the whole semester. And so I suggest you go and look at the review slides for each exam, look at the old homeworks. All of those things will help you, especially, you know, maybe section 1 and 2, the stuff that's a little older that you'll need to study up on. But now is the time to start making a good plan for your final studying. I will have extra office hours next week and a couple of office hours finals week. But of course, you're always welcome to make an appointment with me, send me an email. I'm happy to Zoom, happy to troubleshoot any problems. And you should know exactly what your grade for the final is, or you should know exactly what your grade is going into the final on Monday. So I'm chewing through exam 4 already. Some of you have it graded. I have a few more to do, but I'm going to push on that, including the iClicker points. So you should know exactly where you stand on Monday. And next week is a great time to sort out any remaining issues. So it's going to be hard to fix those finals week. You know, Penn State asked that I get in grades pronto Friday night or Saturday or Sunday. So it's really hard to fix stuff during finals week because I got to put stuff in and record it. But it's a lot easier to fix things this coming week. So let's talk. If you have any questions, we'll sort that out. Any questions or issues? Finals on Canvas, it's going to be a little bit longer than a regular exam, but it's going to be exactly the same format. Multiple choice, and then scan in a written answer. It's just going to be a bit longer. So instead of 20 questions, maybe it's going to be 30, 33 questions, something like that. Instead of 3 written questions, maybe it's going to be 5 or 6 written questions. And so the final is just a little bit bigger version of the exams you've already taken. And I haven't seen any major problems on the exams. You know, just get things submitted in the right issue. But I think there was one bad question on exam 4, so I think everyone's going to get a free point, but I need to look at that. So don't worry if you were confused on a diagram. For some reason, the internet didn't put the right diagram in the right question, or maybe I clicked the wrong button. You know, that happens. But I'm looking at that this weekend, and so there might be a freebie on exam 4. Any questions or any issues? Yes. The final will be open Wednesday, Thursday, and Friday. We have some people graduating. We have people at non-UP campuses that are Commonwealth campuses. We have some people that are overloaded. And so rather than trying to open up individual windows for everyone, because I have to do that manually, the exam's going to be open Wednesday, Thursday, and Friday. Of course, it's timed, so you don't get all day to take the exam, just like the regular exam. And so make sure you have 2.5 hours, sit down, get it done, all of that stuff. But you can take it at your discretion, and it will be open solid. So I'll open it at 7 a.m. Wednesday, and I will close it at 11 p.m. on Friday. I suggest you not take it at 2 o'clock in the morning. You know, that's probably not your most awake time, no matter how you feel at 2 a.m. But, you know, you can take it whenever you want. So it's not going to open, close, open, close. Got that? Yeah, is that cool? Yes. It's going to be a little bit longer than a regular exam, maybe 30, 33, 35 questions. probably won't be 40. So it's not going to be double a regular exam, but you know, the final period is an hour and 50 minutes, I think. And a regular exam period is 50 minutes, although I give you a little bit extra. So, you know, you want to set aside 2.5 hours to like get the final done. It's going to be bigger, but it's not going to be crazy. I mean, you're not going to be rushing to finish it if you have studied, if you remember some of the basic concepts, if you review all the exam review slides. I mean, you know, I'm not going to go into the nitty gritty details since it's comprehensive, but you know, you can bet I'm going to ask you the difference between step growth, chain growth. I'm going to ask you about what monomers, polymers, flash transition temperature, you know, all the basic stuff that really make up the foundation of polymer science that we've talked about in this class. I'm going to try and get that on the final. Yeah. So I'm not going to like get the gotcha questions, or I'm not going to ask you questions on things I probably haven't tested you or given you homework problems on. And so, you know, the comprehensive final is really going to be, can you think about the whole class together and connect the concepts? Yes.
Are you going to do a practice exam like you have?
I don't know if I have a practice exam for the final. I'll take a look. Of course, good practice exams for the final are the practice exams for all the exams. Yeah, because the final is not anything special. It's just over the whole semester. So I don't know that I do have a practice exam for the final, but I'll sort that out. We'll talk about the final again on Monday, because it's really good to start thinking about the final exam ahead of time. Other questions? Okay, and like I said, if you run into problems at the end of the semester, the earlier I know, the better it is, because it's really hard to fix things during finals week. So we just need to plan ahead. All right, so in these last few lectures, we're going to talk about smart materials. We're going to talk about biomaterials. We're going to talk about 3D printing. We're going to talk about cool stuff that polymers do, and we're going to relate some of this cool stuff to the concepts in class. Now, if you're interested in something, superconducting polymers, if you're interested in some strange polymer synthesis, if you want to know about XYZ, just shoot me an email and say, hey, I'd like to see a couple slides on this. You know, I'm happy to discuss whatever you want to discuss, as long as we can relate it back to the core concepts of polymer science. And so I'll tell you about that today in the realm of smart materials. So the question is, what is a smart material? And a smart material has usually a multiplicity of functions, which means it's strong but resilient, or it can change shape or change color or respond to a stimulus. And so there's a lot of modern polymer science in smart materials because we get a lot of inspiration from nature. And so let me see if this video works. After we see some ads.
Check out this Verbo.
Oh, man.
Look at me. Come on, here I am.
There we go. So this is a cuttlefish in the ocean, and you see it's just doing its thing. And of course, cuttlefish is all soft and squishy. It's mostly polymer. And then they're gonna, or it's gonna startle, and then it's gonna change color to be more like the bottom, right? So it's really easy to see this fish against the sand when it's dark or it's over the rock, so it's modeled like the rock is. But as it moves over the lighter sand, it's gonna change color to camouflage itself. And that's all due to how the skin of the cuttlefish is structured and the soft material response of the cuttlefish. And there's a lot of really interesting things like this in nature, and we'd like to be able to do that with synthetic polymers and control it. All right, thanks, cuttlefish. So that's a smart material. It just happens to be part of an animal. And so we have this idea of active and adaptive materials. So usually when we build a building out of steel and glass, it just sits there, right? I mean, it slowly settles and other things like that. But what if we had shades when it was really sunny out? The shades would just automatically close without any motors, without any sensors. Or if it was hot and humid, maybe the windows would automatically open in this building. Of course, lights turn on, shades open and close, but that's usually done mechanically. So there's a sensor, there's a motor, there's systems to break down, there's expensive components that need to be replaced. But if we can build the function into the material in the first place, you know, the cuttlefish, all that sensing and changing is done automatically. What if we could build some of those same things for human use? And we already have things like self-healing materials. We already have scratch resistant surfaces. And so we're slowly starting to get there in terms of using these active and adaptive materials in our daily lives. So things to think about: what's the sensitivity, or what is the trigger for the material? So how do you get the material to change? And we'll go through a couple of examples of this. And what is the molecular mechanism that leads to that change? So you just can't say, well, I hope this material changes like this. You need to build that into the molecules, and I'll show you about that. And also, what is the response? So what do you want the material to do? Change color, move, get harder, get softer, and how do you program that into the molecules? All right. So there's a bunch of different ways that this can be done. I'm just going to show you a couple because they really relate to class. But there can be chemically responsive polymers. We've already talked about pH responsive polymers, right? And you remember that mechanism. That's a stimuli responsive smart material if you can build that mechanism into a material. Temperature responsive, light responsive, I'll show you an example of that. Mechanoresponsive, so say you bend a polymer sample and it changes color, showing you that, oh, I've been bent, or this is a strain. Has anyone ever used that pressure paper where you put the paper in between two plates and clamp it and it tells you where the pressure points are? Yeah, so that paper is filled with little capsules that break depending on the pressure. But what if you had a cell phone that could measure strain optically? So you know, if you bend your cell phone or if you drop it or something, it shows you where the material has been deformed. That could be very useful for lots of different things. Electric field responsive, shape memory polymers, all of this stuff. So there's lots of cool ways to think about how do you get materials to change depending on these stimuli or depending on what they're sensitive to. And this can be used in drug delivery. So has anyone heard of like controlled release capsules? You know, you take this capsule and it doesn't dissolve in your stomach. Maybe it dissolves in your small intestine. That's a form of smart material. And it's sensing the pH. So it doesn't dissolve in the pH of your stomach, but it dissolves in the lower pH of your lower intestine. In cancer treatment, they use some chemotherapy drugs that have a target on them that goes right to the tumor. So tumors have special molecules based on the tumor cells and everything else. If you build that target into chemotherapy drugs, they can go find the tumor, and then the drug sits right there in the tumor where it's needed. Artificial muscles, this is a big one because we'd like to make robots that are more like humans, and so we'd like to make soft robots. Capture and release, so if we're going to capture CO2 and then release it in terms of putting it into a product or underground, that's a big area right now. Self-cleaning surfaces, so if you notice, some skyscrapers don't get their windows cleaned in the traditional way where they send a person down to clean the windows. They have TiO2 on the surface, which is a UV photosensitized material. And so you have self-cleaning windows, robots, camouflage, etc. So we've already talked about stimuli responsive hydrogels, but hydrogels are one of the main interest areas because if we could make robots out of hydrogels, they start to look a lot like cuttlefish, and that's pretty interesting. And so, you know, the story of sodium polyacrylate, we build in this ionic function in order to get the material to expand when we expose it to water. So if we add water, we get ion dissociation and the chain expands. So sodium polyacrylate is a smart material. And the stimulus, or the stimulus, is water. The stimulus can also be ions, because if we add ions to the already expanded polymer, we screen it and it shrinks. And so this is a very simple example of a polymer that responds to its environment. We just have to figure out what to do with it. And so we already saw this example, and I just wanted to remind you of this pH responsive polymer that now swells and shrinks depending on the proton concentration. So that's the basic idea. I mean, we've already learned some things about responsive polymers. You know, polystyrene, it's hard to think about, okay, how do we get polystyrene to respond to its environment? Polyethylene, well, it doesn't really have a response built in, but what we're looking for is polymers that have some sort of responsive unit. So we need some kind of responsive unit. So a lot of our garden variety polymers don't do this, but sodium polyacrylate is pretty common and it's used in interesting applications. Another functional unit that's used a lot in responsive polymers is this cis-trans isomerization of this azobenzene compound. And so this is azo, and this azo unit, or this azobenzene, undergoes trans, right? This is trans configuration, and this is cis configuration in response to light. So lambda 1, that wavelength is between 330 to 380 nanometers. So you shine a UV light on this azobenzene unit, and it goes from trans configuration to cis. And then you shine a longer wavelength, greater than 420, or you heat it up, and it goes back from cis to trans. So what effect would this cis-trans isomerization have? What are we really changing in the polymer when we do cis-trans isomerization? So if we think about all trans conformation or transplanar conformation, right? And we change some of those bonds to cis, what's the general effect of that? What's that? Well, the crystallinity may change, right? But if you're locked into a crystal, you're going to have a hard time rearranging. What else might change?
The overall chain length.
The length, right? So if we start to put in some cis bonds, and if we had an exact molecular model, the cis will shorten the chains, because you look at the sort of the phenyl or the paraphenyl position here and the paraphenyl position here. You can see in this diagram that it shortens almost by a factor of 2. And so if we're changing the effective length of the polymer chain, that can build up stress in the polymer. It can be used for motion of the polymer. It can be used to collapse hydrogels and other things like that. And so this is a really interesting article, and it's got a great title: Polymers Move in Response to Light. And we haven't talked about that in this class so far, right? And so that's a really interesting phenomenon that's built from this functional unit. And it turns out that there's lots of really interesting synthetic ways that you can turn azobenzene into a polymer. So you could make these R groups esters, right? You could make these amides. You could think about making a step growth polymer from this monomer, and all you need to do is build that azobenzene unit into the backbone to get this function. So this is your functional or stimuli and you can build this in. So say on the written part of the final, I say, well, this is your functional unit, this azobenzene, and I give you the structure with 2 R groups. What type of polymerization would you choose to build this into the backbone where the cis-trans isomerization happens? How would you make a monomer out of this functional unit in order to get the polymer to do what we want it to do? What might you do? Let's stick with the type of polymerization first. So first off, whoops, it's an R, kind of. So here's azobenzene. First off, what type of polymerization would it take to get this thing into the backbone? What's the general class of polymer? Step growth or chain growth? Got 1 vote for chain. Anyone vote for step? Got 1 vote for step. All right. Where are the other 40 votes? So in order to connect 2 ends of this functional unit together, what type of polymerization does that really look like? Chain growth or step growth, right? Chain growth, you usually have something like this, right? Where you're not connecting 2 ends of the functional unit, you're just connecting this double bond, right? So chain growth is likely out, except of course, if you turn these R groups into vinyl groups, and you could think about putting a vinyl here and a vinyl here, but then that's a cross-linker. That's a little bit trickier. But maybe we turn this into an alcohol or a diol. So we can, do some step growth. What should we combine this with to make a polymer? What do you think? What's the other monomer that we might want to use? We probably don't want to use styrene, right? Because if this is our functional group, if it's a diol, this styrene is not going to react with those, right? So what's another monomer that we might want to pick that reacts with this diol? Yeah. Carboxylic acid is a good one. So we could have, carboxylic acid. And then how do we get that polymer to work? First, what type of polymer do we form when we combine a dicarboxylic acid with the diol? Polyester. And what small molecule do we lose to make that polyester? Water. So, or we could use a diacid chloride, right? Something like that to make a polyester. We could try and make a polyether if we could get those alcohol groups to condense as well. And so that's, advanced polymer making. But as soon as we pick the diol, you should know what functional monomers to pair up with that diol and what are the possible polymers to make. Or if I give you a diacid chloride or a diamine and I say, this is one monomer to make a polymer, give me the second monomer, name that polymer, write out the chemical structure. That's what I'm looking for. You've done that before in section 1 and section 2. It's just time to refresh that. Any questions or comments? Okay, don't forget about making polymers and monomers. That's going to be really important. And so the way that they did this is they actually used acrylate polymerization. So they did turn it into a chain growth monomer, and then they did free radical polymerization of these acrylates in order to get this mechanically responsive polymer. So you could see as they shine different types of light on this material, they can get this polymer to bend and move. So, and again, another really cool title. Of course, with these responsive polymers, the titles can be really interesting. And we've never seen this sort of behavior before, right? We've never shown light on a polymer other than to do photoinduced free radical polymerization. So this is a new function that's built into polymers, and it's all because of this functional azobenzene unit right there. All right. There's other types of light responses that we can use. So this is cis-trans isomerization. In this case, this molecule right here, as you shine light on it, you go from this thing right here to this. What is the responsiveness of this monomer, or what function does this monomer have that we can take advantage of? If we go from a monomer here, shine light on it, and we get this monomer, what is that monomer doing? Ionization, or it's making something that starts to look like a polyelectrolyte, right? So you can get out your clickers. So this is a functional unit that we're going to build into a polymer, and the question is, what can we do with that? And so we make a water-soluble gel using this monomer. So what type of polymerization are we going to do with this function on there? Free radical polymerization, some sort of chain growth, right? Because this monomer looks just like this. It just turns out that that R group is gigantic, right? We can't really polymerize off these nitrogens because we don't know any polymerization techniques unless that's a primary amine. So we're going to do something like free radical polymerization or something like that. And so when we take this gel that's initially in this state and we shine light on it, does this gel swell or shrink? So remember, our reaction is shown by the arrow going this way. And that lambda indicates we're shining light on the neutral gel, and it's going to ionize. So what happens? 40, we have about 40, maybe 43 out there. Anyone else? And so it's going to swell because of this polyelectrolyte effect. And so this is interesting because this monomer initially was not ionic, right? So we shine light on it, it becomes ionic, and this thing swells. And so that's pretty cool. There's other types of light responsive chemistry. It turns out that if you're really interested in chemistry, photochemistry is pretty cool. And so when we go from these molecules, and these are cinemates, to this, what are we doing in the presence of light? So when we shine light on these two molecules, what happens? What are those big thick lines? What do they represent? Or how do we get them in the first place? Yes.
Are they new bonds?
They're new cross links. That's right, because we have double bonds here, right? And so what happens when you excite these double bonds is that you get electrons. Oh, those are half arrows, sorry. You get an electron that goes here an electron that goes here, one here, and one here. And you have single bonds now that form a cross-link junction between these two chains. And why are cross-links important? What happens in polymers, or why do polymers care about cross-links? Those polymers can get stiffer, right? So you don't have as much flow in elastomers. The polymer can get harder. It's resistant to heat. Remember, thermosets, you can't remold, but thermoplastics you can. So you can go from thermoplastic to thermoset. You might be able to go from elastomer to a stiffer polymer. So there's lots of interesting things that you could do when you cross-link a polymer. And what's special about this is that you can take the cross-links away. So these are reversible covalent cross-links. And you don't see a lot of that, right? So you all know about reversible reactions from general chemistry, but you don't study a lot of covalent bonds that you can make in one direction and then break going in the other direction in a reversible manner, right? To break covalent bonds, you're usually going downhill in energy to make some different compound, but now we have reversible covalent bonding. All right. The other thing that we haven't talked a lot about is breaking chains. So taking a polymer chain and taking that chain and actually breaking the covalent bond in the backbone. So we've talked about strain to break of a material. We've talked about ultimate tensile strength and things like that. But when you break a big polymer sample, like you break a sample of a tensile bar or something like that, usually you're just disentangling the chains, and a couple of them may break, but not a lot. So why don't chains usually break like this? I just told you when you break a polymer sample, you usually disentangle the chains and things like that. But why don't you just break a polymer in half? Yeah.
The interactions, like the intramolecular interactions between the chain itself, stronger than the ones between the chains next to each other.
Perfect. The intramolecular interactions between the chains are weaker than the the intermolecular interactions are weaker than the within the chain forces. What is the main force within a chain that holds a polymer together? What's that called? Covalent bond, right? So this is breaking a covalent bond. And covalent bonds are stronger than most IMFs. So that's why the intermolecular forces allow the chains just to slide past one another. And so when you break a polymer sample, the chains just go their separate ways. But for a particularly entangled polymer or a designed polymer that you pull on specifically, you can start to rupture a covalent bond. And if you rupture this covalent bond right here, what makes up a covalent bond? So when we draw that solid line, what does that mean? There's two electrons, right? And an unpaired electron, if we break a covalent bond, what are these species right there when we've broken the bond? Radicals, free radicals, right? They're connected to the end of the chain. And so it looks like a propagating chain, right? We saw polymer chains with free radicals on the end of them. And so you can do things with that. So this is a lot like propagating chains. So they can react. Now, usually when you have a polymer sample, you don't have a lot of monomer around. I mean, if you had a bunch of monomer, you could maybe make some more polymer and heal that chain. That would be very interesting. They, of course, can combine by combination or disproportionation, right? Because those two radicals are sitting right there. But one of the things that people have thought about is, can you use these radicals to do other things? And one of the things that this group has worked on, and this is just a really cool paper, is that if you have some sort of compound that fluoresces in the presence of radicals. So what happens is that you cleave this boronate ester with a radical, and you get this fluorescent compound right here. And so now if you're looking, I mean, they have to do it in the dark because the light generation is small. But when you squeeze this polymer and you have a little water around and peroxide, you can start to get this fluorescent response. So you can see the material being damaged. And this is really interesting. So there's color responsive ways to do this. This is a fluorescent mechanism, but this allows you to monitor damage in a polymer. So why might you want to know if a polymer is damaged? It can affect its structure and properties. So one of the big things that are made out of polymers now is the Boeing 777, right? And so, or 787, right? The Dreamliner is more than 50% plastic. And so you'd really like to know if that polymer is damaged or not before you go up in that airplane. Or you'd really like to know if some component is starting to wear out. And so polymers that are able to report their damage are really interesting in terms of structural health, in terms of making sure that that component is at its optimum performance. And of course, this is not used in an airplane right now, or it's not used in a fiberglass composite, but this is the way some people are inventing new polymers for new functions. Okay, this is another one right here. And so what they do is they build in this fluorescent responsive unit into this polymer chain. So as you stretch it, it reports where it's been stretched. So reports. So you're gonna strain this thing like this. So it's a different mechanism than those little capsules in pressure paper. This is an intrinsic part of the molecule, and so you can get this really interesting function. Questions or comments? All right. Okay, we have some more mechanoresponsive polymer, but the question is, here's a clicker question. So we're going to take this polymer, and this dibromocyclopropane is closed when there's no stress, but when you pull on this polymer chain, this is going to open. And the question is, how does the contour length change when you pull on this polymer? So you get stress activated isomerization from this state, state one, to state two. So the question is, what is the contour length? And does it increase, decrease, or doesn't change? And so we have a complicated situation, but you just have to remember what contour length is, and you can solve this one. So what is the contour length of a polymer? What does it look like schematically? So we have our generic polymer. And which one is the contour length? Follows the bonds, right? So this is the contour length. What's this length right here? Fully extended chain. I heard end-to-end distance and other things like that. Make sure you look up how to calculate the mean free end-to-end distance or the root mean squared end-to-end distance for different situations. But the simple ones are contour length and fully extended chain. So when you go from state 1 to state 2, if you notice, there are 1, 2, 3, 4 carbons in this monomer unit. And there's 1, 2, 3, 4, 5 carbons in this monomer unit. So does the contour length go up or down? It increases, that's right. And so, you know, you don't need to know anything about how this stress activation works and how we change the polymer chain due to this mechanochemistry, but by remembering that the contour length traces the backbone, automatically the contour length is higher when we have 5 atoms in the repeat unit versus 4 atoms in the backbone of the repeat unit. Because the substituents don't matter for contour length, right? We're just tracing the polymer backbone. Does the degree of polymerization change? No, same monomer, right? We have N, or same number of monomers. We have N here, we have N here. Molecular weight doesn't change. We're not spitting out any small molecules or anything like that. And so this is a really interesting stress activated isomerization. All right. So we're going to cover just a couple more things. There are such things called shape memory polymers. So rather than using stimulus like this light responsive polymer to, if I can get back to the light responsive polymer, to change the shape of a polymer, you can fold up a polymer, and depending on how you heat it and depending on the processing, you can get this shape memory effect. And a lot of you have used shape memory polymers before. Where?
Braces.
Great.
Parts of the wire that goes through that heat it up to get the shape they want.
So that's shape memory metal, right? Yeah. So what's a shape memory polymer that you've used? Think back. Those are not shape memory. Those are just shape moldable, right? They don't spring back. So memory foam is kind of a shape memory polymer. Rubber bands are kind of shape memory. You stretch it, but what have you cut out with the scissors, colored, heated up, and then it's a totally different thing. You make a Christmas ornament out. Shrinky dinks. That's right. So if you've never used a shrinky dink, you can go YouTube it. But what shrinky dinks are is they sell you a sheet of shape memory polymer that's been programmed in a very flat big sheet. It looks like a computer transparency if you know what one of those things are. And then you color it, you cut it out, and then you put it in the oven and it shrinks like by 5x. And the colors get really bright, looks like stained glass. They get thick, they get hard, like a hard piece of plastic. My kids have made Christmas ornaments out of them and stuff like that. But that's a shape memory polymer that they programmed and put in a box and sold to you. And that shape memory effect is not activated until you put it in the oven. So there's lots of cool things to do with shape memory polymers, especially shape memory polymers that respond around body temperature. So if you ever have to get a heart stent, some of those are shape memory polymers because they'll pop open when they insert it into your aorta to pop open your blood vessel. Those are made out of shape memory polymers. There's cool stuff, self-tying knots. There's other biomedical applications for this, and you can read all about that. The last shape memory idea that I want to talk about, or at least responsive polymer that I want to talk about, is additive manufacturing. And there's some really cool videos about this. So what they're going to do in this video is that they're going to make this two-dimensional flower shape out of water responsive polymer. So this is a swellable hydrogel. So you'll see the printing, and then you'll see what this flower does when it's exposed to water. It's got great YouTube music, but this is all printed perfectly flat. So there's a real famous 3D printer at Harvard. Her name is Jennifer Lewis. And if you've ever seen the Nova special on origami, there's a scientist on that special called Mahadavan. He did all the mathematics to figure out what to print in the first place. You should check out that origami thing on YouTube. It's really cool. Okay, so this is not just making a pretty shape. These are printed in very specific ways in order to get this material to respond how they want once the printing is done. So this is not necessarily origami because you're not starting with just a flat square sheet. But if you take this, if you take this flat structure with all these different lines pointing in different directions, all those polymers are going to swell differently. And so depending on how that swelling's done, you can get a three-dimensional shape. So when they put this in water, now you can see this curling, you can see this three-dimensional shape coming. They call it 4 dimensions because it will respond to its environment just with a swellable hydrogel. And this happens in lots of different ways in 3D printing. So this is one more example.
Check out this
After we get
verbal.
there.
Look
Oh wait,
at
that's not the
me.
example.
Come on,
Well,
here I am.
this is one, yeah, this is one nice example right here. Oh, if I can do that the right thing. So notice when they put this in water, this is all compact. So it's very small. It's all printed, 3D printed in a very special way, and it's actually going to go into warm water and swell. And then it swells into the letters ETH, which is a big research university in Switzerland. But now this is a responsive polymer because all of these unit cells pop open and give you some final shape. And so people are interested in using this, say, for space antennas. How do you unfold things in space? Of course, what big thing have we unfolded in space recently? James Webb Telescope. It didn't use smart materials. It used motors and other things like that. But the next things are going to unfold on their own with some sort of stimulus. All right, I'll see you on Monday.